This is how the Bi-Cmos structure looks whenever we try to design or fabricate any kind of Bi-Cmos device, where you will be having NMOS, PMOS, and this is a NPN BJT. It means that you are supposed to create 3 different wells here. One well, this is one well, this is another well, and this is a third well. So it's like the Bi-Cmos structure will be of triple well process, where you'll be using, or you'll be manufacturing, or you'll be fabricating a transistor by using the triple well process. And these are the terminals of the NMOS: source, gate, and drain. And we know that for this one, the source and drain for the NMOS will be of a N type of diffusion. That is the N type of impurities will be used. And for the PMOS, the source and drain will be of P type of impurities will be used in order to create this one. And this red color indicates that it is a polysilicon which is used as a gate terminal in this both the cases. And for this one, for the NPN BJT here, the 3 terminals are collector, base, and emitter. The emitter has been designed in the well like a NPN, it's of N type of impurities have been used. N plus impurities have been used here in order to create, or in order to design or make this emitter terminal. And this N well collector, which is where into this N well collector only both the base and emitters have been created. For the base has been created in the N well collector, and within this N well collector another well has been created, which is of N plus emitter, which is of N plus impurities, which is basically or mostly used for the emitter part. And this entire NPN design has been used upon the N plus buried layer, just as we have seen this one about fabrication of this NPN BJT in the previous slides. And this entire structure, we know that for CMOS structure we need the substrate, and the main substrate for this Bi-Cmos will be of P type of substrate. And in the P type of substrate we'll be using another P type of substrate. That's we call it an epitaxy, P type of epitaxy. Inside this P type of epitaxy only we'll be designing our CMOS, and this NMOS has been designed in N well buried layer. Now let us see the fabrication steps for the Bi-Cmos technology. First one, it's a P substrate formation. The base will be of P type. For any kind of Bi-Cmos technologies, the base, we are supposed to create the base, that's a P type of substrate should be formed. And later after that one, almost the fabrication of this Bi-Cmos will be similar to the CMOS fabrication. So that's first we'll be creating a P type of substrate. Then later this P type of substrate has been covered, or it will be another layer will be formed upon the P type substrate by oxidation process. So in the oxidation process, SiO2 comes into picture here. It's an oxidation of silicon takes place. This silicon takes place in the presence of oxygen at high temperatures. So that's why SiO2 layer has been used, and this oxide layer will act as an insulator, which acts as an insulator or barrier for this entire design, in order to protect the design from further impurities to enter into this substrate, or else for further any kind of layers which can diffuse into this one. So this one will act as a barrier. And next, after that one, the window formation has been done. Here the window formation is done. Window formation means what again? The etching process of this SiO2 layer has been done, and after the etching process only the window formation has been done. Then later after the window formation, here the impurities are been diffused. N type of impurities are been diffused in order to make it as an N plus buried layer. Into this P type of substrate, first we'll create a window, and then into that window at high temperatures, at very high temperatures, it's like nearly some thousands of degrees Celsius at this particular substrate will be heated in an oven, and at that particular time N type of impurities will be diffused in order to form it as an N plus buried layer. And next one, P plus epitaxy layer is being grown in this P substrate. And onto this one, then again we'll be growing a P plus epitaxy layer. This is a region where the CMOS will be designed, or CMOS will be created, and this is a region where the NPN BJT will be created. So in the P plus epitaxy layer, we'll be creating the CMOS device. And after that, the entire surface is covered with the oxide, and the two windows have been formed through the oxide layer. Here again, the entire surface after forming of this P epitaxy and also N plus buried region, the entire will be the substrate will be covered with the oxide SiO2 layer. It means again the SiO2 layer will be created, and after that creating of the SiO2 layer, again the two windows have been formed. Two windows have been formed. Why do we need to create these two windows? Because we need to diffuse the impurities in order to form the two terminals of the BJT, and also here we are supposed to form the terminals of the PMOS device. So that's why we have formed here two windows. You can see here now. This is one here. N well has been formed for the collector part, and this is a N well which has been formed for the PMOS. We know that a PMOS has been designed in the N well. So that's why if N well has been created, means here we will be forming the PMOS device, and this is a collector region of the BJT. And these regions have been formed with the help of diffusion process only. We'll be diffusing the impurities in order to form the N well. And later the third window also been formed here. This third window will be used as an region where we will be forming the NMOS device. So this is how the three windows are formed through the oxide region or the oxide layer in order to form the three active regions, three active devices. That's for NMOS, PMOS, and also BJT, NPN BJT. And after that one, we'll be growing the this gate region. For the gate region, we'll be growing. The entire surface is now covered with the Thinox. We know that Thinox is nothing else but it's a thin oxide layer, thin SiO2 layer is been created, which is of only 1 mm. 1 mm size of oxide layer will be created, and after the etching will be done. After etching again, then the polysilicon will be laid in order to pattern the gate terminals of PMOS and also NMOS devices. And in the next process, in the third window, we will be doping the P type of impurities in order to form the base terminal of the BJT. Again, this region will be subjected to very high temperature. At the high temperature, you will be doping the P type of impurities, and this P type of impurities will be acting as a base terminal for the BJT. And this has been done here inside this N-well collector. So N-well acts like a collector terminal. This N-well will act as a collector, and now we are trying to design the base of the BJT. And you can see it now. Here the N type of impurities have been doped here. The N type of impurities are heavily doped to form first one, the source and drain regions of the NMOS. The N type of diffusion has been done in order to form the source and drain regions. Then later here, N type of impurities have been formed in order to form the emitter region. So all at a time, the N type of impurities will be doped here in order to form the source terminal of the BJT. And again into the N-well collector region for the contact purpose. This is a region where we mainly use for the contact purposes. So we'll be doping here also in order to have the contact purpose region. The next one. The P type of impurities have been doped here. The P type of impurities have been doped in order to form the terminals, that's the source and drain terminals of the PMOS. And the doping concentrations are same like whatever we have studied in CMOS technology. So the source and drain regions have been formed with the help of this P type of impurities. And again, the P type of impurities also been doped here, which will act as the P region for the contact purpose. So it will act as a P region for the contact purpose. So this is a contact region of the N type of impurities, and this is a contact region of the P type of impurities. Then now, after this doping, the entire surface is now covered with a thick oxide layer. It is covered with a thick oxide layer. So again, to protect the entire structure from additional doping or else additional formation of any kind of layer. So we are again creating a thick oxide layer on the entire substrate. And after creating of the entire oxide layer on the entire substrate, then the entire surface is covered with a thick oxide layer, and it is patterned for the contact cuts. Wherever you want the terminals, that's a source, drain, and gate terminals are to be formed, there we will be making the contact cuts. It means that you'll be etching off the SiO2 layer in order to form the contact cuts. So this will act as a space or the region where the metal layers can be created. The metals can be used in order to form the three terminals of the three devices. There's a PMOS, NMOS, and the BJT, NPN BJT. And you can see it now. This is how the entire Bi-Cmos integrated, or the Bi-Cmos transistor has been formed here. The metal contacts have been formed here. Wherever you want this one, wherever the contact cuts have been used, there will be diffusing the metals, mostly like aluminum has been used here in order to form these three terminals. And after diffusing that one, wherever you don't want, it's not like you'll be diffusing only in that particular region. On the entire surface, there'll be creating this metal region. It's like it is called as a metallization layer. Metallization layer will be created, and wherever you don't want that metal, it will be etched off. Here in this region, it will be etched off again. Wherever you don't want that metal, it will be etched off. And wherever it is required for the three terminals, there only it will be put. And that these metals will act as the terminals of the devices. So this is a source, gate, and drain terminal of the NMOS, source, gate, and drain terminal of PMOS, and collector, base, and emitter of the NPN BJT. We can see here now this metal region is being directly connected to the particular diffusion part. This source of the NMOS and the drain of NMOS is connected directly to N diffusion region. It means that the contact has been done, the contact cut has been done until this one. The entire SiO2 has been removed until this part, and so that the metal can touch this diffusion layers. So this is how the metallization has been done in order to form the three terminals of the devices. So this is regarding what is meant by, say, BJT has been fabricated, and later what are the advantages and disadvantages of BJT, what are the advantages and disadvantages of CMOS technology, and how a Bi-Cmos device can be fabricated.